Okay, so using the Bohr equation, which is right here, I'm just going to go ahead and insert the information. So it says the electron in a hydrogen atom is in the n equals 2, so n is energy level, so it's saying it's in the second energy level. And then it says it drops to ground state. So ground state is energy level 1. So ground state is n equals 1. And this is where it started. So that's my n initial. And then this is my n final because my ground state is where it finished because it dropped there. And it says a photon is emitted. What is the wavelength of the photon? Well, I know from this equation I can't get wavelength, but I can get energy. And then I know from my other equations I can use energy to find wavelength. And then I can look at it on the electromagnetic spectrum. So here, where it says delta E, that's what I'm trying to find. And then it says negative R. So R is my constant, the Rydberg constant. So 2.18 times 10 to the negative 18. And I'm going to multiply that by 1 over n final squared. So n final is my n equals 1, so that's 1 squared, and then minus 1 over n squared initial, oopsie, not n, I mean that's what it says in here, it says n squared initial, but n initial was here, so that's 2 squared. So I'm going to go ahead and solve that. That gives me negative 2.18 times 10 to the negative 18 times 0.75. And then when I multiply those together, my delta E gives me negative 1.635 times 10 to the negative 18. And then energy is measured in joules. The unit was joules here for the constant. We had joules, and then the energy levels don't have units. Okay, so there I am. This negative, we can't actually have a negative amount of energy. Energy, like when you're measuring an amount of it, it can only be positive. Negative just means that energy is being emitted, which makes sense, right? If we have the nucleus of an atom, and then we have all of these electrons, and this is ground state where n equals 1, this is the next one where n equals 2, and I have an electron here, and it's falling to ground state, that means it's giving off energy. If it's absorbing, like to go to a higher energy level, that means energy is going in. So since energy is going out, we then have the negative sign. If it was going n in, it would be positive. So that negative is not going to carry over to our next equations. So we know our next equation is E equals the frequency times Planck's constant. So I know my E is negative, again, we're not carrying over the negative because that just means emitted. The value of E was 1.635 times 10 to the negative 18, and that's going to equal my frequency, which I don't know, that's what I'm going to find, and then my Planck's constant, which is 6.626 times 10 to the negative 34. So I'm going to go ahead and solve for my frequency by dividing both sides by 6.626 times 10 to the negative 34. And I get the frequency of 2.4, since I'm dealing with 4 sig figs. I had 3 here. These don't count as sig figs. These energy levels don't count. I had 3 here, but that was a constant. So technically I don't really have sig figs in this problem, so I'm just going to keep decimals, but since this number just came out to like, I don't know, 15, I'm just going to stick with the 4 that I already have. So 2.468 times 10 to the 15. So I'm going to plug that into my next equation, which is C equals wavelength times frequency. So now I can solve for wavelength, which if you remember back in the question, it says what is the wavelength of the photon. So now I can solve for wavelength. I'm going to take my speed of light and divide it by frequency to get my wavelength. So my speed of light was 3.00 times 10 to the 8 divided by my frequency, which is 2.468 times 10 to the 15th power, and I get 1.21 times 10 to the negative 7, and that's in meters. Usually we report wavelength in nanometers, so it'd be 121 nanometers, but in order to look it up on the electromagnetic spectrum, sometimes you need meters and sometimes you need nanometers. It kind of just depends on what picture you're looking at. So 1.21 times 10 to the negative 7. So here you can see the wavelength here is being measured in meters. So 1.21 times 10 to the negative 7. Notice the visible light range goes from 4 times 10 to the negative 7 to probably 8 is about right there. So 1.1 would be down, or 1.12 times 10 to the negative 7 would be somewhere down here. So just past the visible range in the ultraviolet range. So the question asked, the second part, what is the wavelength? Well, it was that 121. And then it says, is this in the visible spectrum? The answer is no, it's in the ultraviolet spectrum. You could, if it was in the visible spectrum, if I got like 5 times 10 to the negative 7, I might ask you what color it is, and then you would say it's sort of a blue-green. Maybe you got 5.5 times 10 to the negative 7, you're right here, like more of a yellow-green. Maybe you got 7, and you were over here at like a red-orange. So I might ask you what color it is based on the wavelength.